Well, good afternoon, everyone, and welcome to TACO Tuesday. We seem to be having some technical difficulties, so for the folks that are out there listening to us right now, we would very much appreciate if you could type something into the question area to see if our system is actually working and that you can hear us and see us okay. That'll help us out here. Yeah, I've got about a half a dozen people saying hello, and they say they can hear me. And you can see my screen. My screen says 4900 magnetic air and dirt separator. Works fine. Okay. So let's get started. My name is Rich Medairos. I'm one of the senior systems engineers here at TACO, and welcome everyone to TACO Tuesday. For those of you who are not familiar with TACO, we are a company that's been in business just over 100 years. Actually, we're into our 102nd year right now. It's owned by the White family, headquartered in Cranston, Rhode Island. And we have working with me today is Ron Falcon. Ron is actually going to monitor the questions as they come in. So Ron, just give me a quick shout out, audio shout out here. Did you see the questions pop up as they
Yep, I do see the questions.
Okay, great. So normally I team up with Brett Zerba to do these TACO Tuesdays, but Brett's having some kind of bizarre technical problem. We don't really know why he can't seem to join us, but he's working on that. A very short introduction to myself, then we'll get into our presentation today. So Ron is going to monitor the questions as they come up, and so he'll ask me to pause periodically to answer the questions. Roughly 24 hours from now, you'll be able to get a recording of this presentation, and for those of you that need certificates, you'll also get an email indicating if you want to get a certificate for today's course. So we're going to get started. I'm going to press a button here and see if I can put that on the side. One more quick thing. Bear with me. Technology is not our friend today. So I want to do one other quick thing here and make sure that the screens are working properly. It always seems that when the world wants to become technically sophisticated, it comes with its own set of issues. So anybody that can see what I'm doing right now, I'm actually testing out my tablet here. Just let me know if you see something handwritten on the screen. And I'm just going to look at the questions. Yeah, great. Okay, so that works. So now that we know that the technology works, let's do the presentation. Okay, so today's discussion is all about the 4900 magnetic air and dirt separator. And let's get into some of the things that we're going to be talking about today. If we can get the screen to advance, that's another challenge. Boy, I tell you, when the world wants to work, and the world wants to be a mess today. Okay. Hang in there, folks. We're going to do our best to get all of these computer things running properly. There it goes. So we like to put in there what is it? How does it work? Why do we need it? Who are our competitors? And some questions. So again, you don't have to wait till the end of this presentation. We actually have two. We're going to be doing magnetic air and dirt separators. We're also going to do flow-through expansion tanks. So let's run over this a little bit here. So I like to answer the question, what is it? And like I put up here on the right-hand side, it's a conventional 4900 air and dirt separator fitted with a manual hand-operated on-off magnet. And the on-off magnet is right here that I'm pointing to right now. This is a pretty slick device. This is a simple handle that rotates the magnet that's inside the air and dirt separator. So it's not electrical. There's no computer chips associated with it. There's no external power source. It just is a very simple mechanical device. And since it's a conventional 4900 air and dirt separator, and you'll see a little bit more detail in a moment. It does have the air vent at the top, and it has a blowdown valve here at the bottom. So as the water flows through this air and dirt separator, it separates out the normal particles of air. Air floats to the top and eventually comes out the vent. The dirt goes down to the bottom. But it has this additional feature of attracting ferrous material. And we're going to go into the detail of this in a couple of seconds here so you can see what's going on. So here's kind of a little diagram of how this works. So on the entering side here, where I have it labeled as water flow in, we'll get the little blue bubbles represent the air, and the little kind of rust-colored bubbles represent the ferrous material. And when the magnet is on internally, it's rotated in the direction that allows it to attract magnetic material. And it coats the magnet. The air separates to the top. If there's any dirt that's non-magnetic, that will separate and fall to the bottom of the tank, and that can be removed by the blowdown valve over here. But initially, when the magnet is on, it attracts this ferrous material. And then obviously when the water leaves the air and dirt separator, it's cleaner than when it's entered, both in terms of the type of material that's removed and the fact that we're also getting rid of the air bubbles that are inside the water flow. Okay, so then when we turn the magnet to the off position, then by gravity, that ferrous material will fall to the bottom of the tank, and then we can open the blowdown valve and get rid of that material. And again, you know, in its initial, let's go back here. I'm going to erase a couple of these things here. Let me erase just a few of these lines so that it doesn't become confusing. Okay, so again, let me go through this one more time. The magnet is on, it attracts the material, and then in the next slide, the magnet is off and the material drops to the bottom of the tank, the air goes to the top, and you get rid of all that material. And so that's fundamentally how it works. Does anybody have any questions out there that even if I can't answer, we've got Ron Falcon on the line with us. He'll also be able to answer. Ron, do we have any questions out there? People are just
Rich, as of right now, we do not have any questions in the chat.
Okay. It does look like we'd have a question. Does the system have to be off when you turn the magnet off? And the answer is no. The system does not have to be on or off when we rotate that magnet. Why can't I go back here? What's going on? Mr. Computer. Mr. Computer is going to kill me today. All right. So that's how it works. Let's go to the next slide here with a little luck. Get this.
I'll have to stand corrected. There was some technical weird thing going on with my chat, and it looks like there are actually several questions here in the chat. Shortly after you mentioned that, they seem to appear.
Okay, well, let's try answering those questions. What are they, Ron?
Yep. So you had that first question: does the system have to be turned off when you turn the magnet off? If you hinder the flow, that would of course prevent flow from particles from working their way through the outlet. So you could certainly isolate or prevent the flow rather at that point and perform your blowdown. There's a question: what are the dimensions of the unit and what are the inlet and outlet sizes? Our 4900 line stretches anywhere from 2-inch connection size all the way up to 36-inch connection size. Body diameters 14-inch up to 60-inch. So a wide range of sizes available for our air and dirt separators, which all have magnetic capabilities. There's another question: how do you turn off the magnet? Literally, you turn the handle from the on to the off position. I think that question may have more to it as far as its function, but maybe we'll address that as we go throughout the presentation. Is it hard to clean the magnet? No, simple as opening up that, turning that magnet handle to the off position and opening up that blow down will force flow over and around the magnet, the shaft sleeve. So the magnet sits within a stainless steel shaft sleeve that when the magnet is deactivated, the active flow and the weight of the particles pushes the particles down toward the blow down valve.
Sounds great. Any other questions, Ron?
We do. We have a few more if you'd like to go through them now.
Yeah, let's pick them up, and that way we won't get too far off track here.
Will we lose any water when we perform a blowdown? When you perform the blowdown, yes, you'll lose some water. Turning the magnet from the on to the off position, you wouldn't lose anything at that point because the magnet is within a sealed shaft sleeve.
And I think it's worth mentioning, Ron, that if the material or the fluid is just straight water, the blowdown can always go to an appropriate drain for for the water. But if it's a propylene glycol or any type of glycol mixture, they might want to have a fluid recovery system so that they don't waste the glycol.
Right, and we actually speak to that in our IOM specific cases for glycol or any fluid that you may not want to waste. We make a suggestion on how you can recapture that. So there is another question here: what are the fluid velocities per size? Of course, a large range, but optimally we're around 4.9 feet per second. That was where the original testing was done on the 4900 with Paul rings, though these have been operated and we've done our own testing well in excess of 6 feet per second for standard velocity designs and 11 feet per second for our high velocity designs.
All right, why don't we move along here, and then if we wind up with some more questions, Ron, we can answer them as they go along. So let's look a little bit about some of the piping arrangements. So you can see how we have it set up here in this first diagram. We have the 4900 air and dirt separator with the magnet, and that can be in line with your piping system. So that's one way of doing it. There is a limit. I believe that we published the limits, right, Ron, in terms of the maximum flow that we recommend through each of the different sizes?
So we do publish a flow rate, which references the 4.9 feet per second nozzle velocity that the independent test studies that were done when we first launched the line. So we do have flow rates published at 4.9 feet per second. But,
okay.
And that's kind of just an optimal range. It doesn't mean that you can't do 5 feet or 5.5 feet or 6 feet. That's just an optimal range.
Okay, so why do we need it? Well, the main reason is that in modern pumping systems, more and more motor pump assemblies, or ECM motors, which stands for electrocommutative motor, they have these permanent magnets, and those permanent magnets will attract ferrous material. That material can build up inside the motor / pump assembly. And over time, that would cause damage to the pump, including the bearings and the internal parts. and ultimately result in premature failure of the pump motor assembly. So that's the main reason of why people are going to these magnetic air and dirt separators to protect equipment that could potentially be compromised because it can attract magnetic material. So again, the ECM motor is probably the major category, but you know, you may also have other situations where you have very fine ferrous material that you don't want to accumulate in your equipment downstream of the air and dirt separator. Okay. Again, why do we need it? Well, again, a couple of things to keep in mind is that these magnets are, I always have trouble pronouncing this, and I'm going to ask Ron to jump in here if I pronounce it incorrectly, but I think it's pronounced neodymium magnets. And
Very good.
did I do a good job, Ron?
You got it.
You got it. So yeah, neodymium magnets, they're very, very powerful magnets. And they do not need to be removed physically from the unit in order to operate it. We have stainless steel Paul rings for premium coalescing efficiency. We can remove particles 150 micron and larger at 3.5 feet per second. And most of our competitors leave behind about 34%. So that's some of the things to take into consideration when you're thinking about an air and dirt separator, especially in the magnetic style. So I guess that pretty much covers what we wanted to talk about on the air and dirt separator. Any last minute questions, Ron, that are out there?
Yep, so we did have a few questions come in. One in particular was how to check the dirt level. And what most folks are doing is measuring pressure drop across the vessel. As that pressure drop increases, they can determine, and that'll actually flow into another question, they can determine what is required for a blowdown schedule. So whatever, particular range that the engineer or the maintenance folks, whatever they feel comfortable with. It might be an increase of 1.5 to 2 psi, and they say, hey, when we hit that point, we want to run a blowdown. When you first install the vessel, it's probably a good idea to be a little bit more frequent with your blowdowns. We're just right away, just to try to see how much you're capturing right in the beginning of having that product installed. And you should start to see that clear out, and then you can increase the frequency of blowdowns that way as well.
Yeah, that's a good point, Ron. I think that's worth repeating. One of the challenges that we're all faced with is the amount of material that's inside of a piping system when it's first started up. And by the way, that's not just when someone's doing a retrofit and they're trying to clean up the material that's in a piping system. You'd be amazed at how much material is floating around inside of a piping system, even if it's brand new pipe. And that happens because of a variety of reasons, most of which is just simply, out of the control of the professionals that are installing this equipment. The pipe, for example, might be stored in a warehouse somewhere, and that warehouse could be at a remote location. This is before the contractor even gets the material or purchase the material, just from suppliers. And it could be in a dusty environment, dusty warehouse. It could pick up a lot of material. Then it's shipped to the site, and sometimes the site doesn't cooperate in terms of storing the material where you'd like to see it stored, and it can pick up all kinds of dust and particles and stuff. And then you put a whole piping system together, and you put the water in it for the first time, and there can be a lot of material. So blowing down quite frequently within the first few weeks of operation is definitely something that we would recommend. to get as much material out as possible. Then when the system has been flushed and cleaned, and most engineering firms will have a specification on how they should go about, how the contractor should go about cleaning out the system. But once that initial cleaning is done, then like Ron said, you can have a more predictable schedule based on pressure drop. So that's all I wanted to add to that, Ron. Any other questions out there?
Yep, we do have another question. What does rotating the magnet do to the system? Do you rotate the magnet prior to blowdown and then restore? As far as the magnet itself is concerned and the handle and its orientation, that magnet handle is going to swing 90 degrees. So it's either going to be in the on or the off position. In the on position, that's when, of course, the magnet would be energized and allow ferrous material to collect on the shaft sleeve. What you would do in the event of maintenance is to turn that magnet from the on to the off position. So that would be a 90-degree rotation. And then open up your blowdown valve, forcing that flow over that shaft sleeve and ferrous material to pour out from the blowdown. There is another question here. Other than ECM motor-driven pumps, are there any other applications where this is an ideal solution?
Well, I think I'd like to add to that question, and that is that any material that builds up in a piping system will be detrimental to equipment. For example, we use the term fouling factor when it comes to heat exchangers. The more material that builds up in the heat exchanger, the more inefficient the heat exchanger becomes, and the more you have to increase the interval of cleaning out the heat exchanger. But that's true of any heat exchanger. So it's not just, for example, a heat exchanger like a shell and tube as part of a system, or a plate and frame as part of a system, but also the heat exchangers that are part of other people's equipment, like a chiller, for example, a chiller barrel that's using both chilled water and condenser water. If it's a water-cooled chiller, those essentially are shell and tube heat exchangers. And if material builds up on the water side of those heat exchangers, then the performance of the equipment will suffer. So chillers, boilers, heat exchangers, anything that has the ability to build up material. And then there's also a phenomenon which may not be a major concern, but it does happen, and that is static electricity. You can get very, very tiny amounts of static electricity, which will cause material to build up on different parts of equipment. So yeah, it will affect just about anything that's in a piping system. Go ahead, Ron. Sorry about
No, that's
being so
okay.
lengthy.
We do have one additional question here. And I'll let you jump in on this one as well. Are there any concerns about magnetic interference in the vicinity of the magnet? For example, corrupting analog sensor signals. I'm not sure if you have any thoughts on that one.
Yeah, to be honest with you, I'm not sure. I mean, I'd have to defer that to someone else that's more versed with, the specific subject of magnets and, and signal devices and controls. But certainly, I would not want to put a controller, adjacent to the magnet. I guess a good rule of thumb would be a few feet away, should have no effect on it whatsoever.
Yeah,
But again, I would defer to someone that had some expertise in this area.
Yeah, and the other thing I think worth mentioning is that magnetics aren't necessarily new in hydronic systems. What is new is the way that we're applying a rare earth magnet set up inside of an air and dirt separator with the on-off configuration. So there are several other versions of magnetic separators out there. There's several standalone magnetic dirt separators out there. Ours is unique in the instance that, again, you don't have to remove the magnet from the vessel. So I'm not hearing of other cases where magnets have caused issues with analog sensor signals. I'd be curious if anyone has, but I have not heard of anything of that sense.
Yeah, this is a great question. I'm glad somebody brought that up. And if anybody out there has information they could send along to us, that would be a huge help. Well, that pretty much covers what we wanted to talk about on the 4900. Any last minute questions, Ron, before we go to the flow through expansion tank?
That looks like that's it on our end.
All right.
Hi, Rich. Hi, Ron. This is Brett.
Hey, Brett, you finally made it through the technology nightmare.
I had to get in touch with the fine IT department at TACO, who they do a wonderful job. And for some reason, they had to change some setting on my computer.
Well, there you go.
So that's as clear as mud.
Clear as mud, as they say. Well, you can help us out if you want to jump in and monitor the questions.
I think Ron's doing a great job. He knows more about this equipment. I hope you mentioned at the beginning that Ron Falcon and his team, led by Ron, are the ones that developed these products. I mean, they did a heck of a job developing these products, you know.
Yeah, I have to admit, I did not mention that because I was so distracted by our technology here. When our technology works, it's a wonderful thing, but when it doesn't work, it's exasperating.
So Ron, give him a little, why did you think of using a magnet all of a sudden? Because you use it in the factory the 24/7, right?
So it's really interesting, and I'm kind of glad you brought that up. We were headed down a path of sort of, I guess, a Me Too type product where folks out there were using magnetics in air and dirt separators, and they were getting specified, and we needed to come up with something. We started down a path and then kind of thought, well, geez, you know, we have so many magnets that we use to haul very heavy plate out on the shop floor because we're doing that every day. And, you know, how cool would it be to just take one of these and slap it on the side of a vessel, put it in the on position, and, you know, it would sit there and collect at least in that location. And we just said that sort of jokingly. And someone said, well, imagine if you could do that inside the vessel. And I said, well, why not? So we really started to, you know, brainstorm and come together and try to understand that sort of technology, and found a way where we could actually implement it and make life a whole lot easier for the contractor or the maintenance folks or anyone who wants to perform a blowdown. It's really tricky when you have to take a magnet assembly and remove it entirely from the vessel, because where those magnets get threaded in, and I'm not talking about our magnet, I'm talking about competitor magnets, where those get threaded in to tanks, there's a lot of carbon steel. In many cases, you're doing this up on a ladder, you're trying to bring tools up with you, you unthread the magnet, you start to pull it out, and it sticks to the vessel. We know because we were trying that approach. They're not really easy to remove. It really makes life a whole lot easier having this on-off style magnet. So it was a technology that we were using in a completely different application, in a completely different way that we were able to pair up with something that the market could use.
You know what that shows us? Sometimes those brainstorming meetings actually have a result that's positive.
Very
It's a
cool.
good
Back to you, Rich. Back to you.
All right, so we're going to go on to our next topic, which is the flow through expansion tank. And so what are we going to cover here? Well, we're going to talk about the same thing. What is it? How does it work? And why do we need it? Who are our competitors? And again, questions. And this time we'll let Brett monitor the questions, and we'll ask Ron to hang by in the background and kind of be the expert witness. And then let Brett tell me to pause periodically, and we'll read through those questions. So let's talk about what is it. So here it is here. And, you know, we're looking at a conventional CA series full acceptance bladder style expansion tank with a special valve and a special fitting inside that allows the water that typically would be stagnant inside of an expansion tank to actually circulate and be removed. So that's basically what it is. So let's go into a little bit more detail here and see how it actually works. So again, grab my handy dandy little marker pen. I say that, Brett, with some kind of confidence that my marker pen is going to be readily available.
I've seen it working.
I've seen it working many times already today. And did it roll off my desk? Well, I tell you, this has been the strangest day for
I think the magnetic separator
the
worked.
magnet separated and stole my pen. Okay, so anyway, I got my pen back. So we have water enters the special valve. So we have a special valve at the top here. And a small percentage of that water is diverted inside this tube. We got this turbulation tube. And that water actually comes out and runs around inside the bladder. Now again, so the black thing here is the full acceptance bladder. That's where the water resides, and then the air is on the outside. It's a conventional CA style expansion tank. And the valve at the top here is specially designed to allow a small amount of water to be diverted inside the tank, causes all kinds of turbulence and stuff. And that way the water does not become stagnant, and then ultimately the water comes out like this. Isn't that cool? That's got a lot of little squiggly lines on it there. Okay. So let's see if we can, let's go back here. This is kind of a repeat of what we just talked about, so I'm not going to go through it in a lot of detail. Again, the water enters the valve at the top. A small amount comes out of the tube at the bottom like this. It causes lots of turbulence inside here, and that water comes out. Now, one of the challenges with any type of hydronic system, whenever you have stagnant water, you run the risk of hazardous biomaterial building up in your water supply. Now, we're not experts in biological material, but we do know that anytime there is stagnant water, there is an increase of the possibility of this hazard material building up. So the whole concept of a flow-through expansion tank is to minimize the amount of stagnant water that's in any HVAC system. So that's the main purpose of this little guy right here. And that's how it works. It's very simple, very straightforward, and it causes water to be turbulent inside the bladder, and so that it's not stagnant. It's a very clever little device. Okay, let's try erasing that, see what happens. Look at that. Holy mackerel, that actually worked. All right, so how do you pipe this thing up? Well, there are a couple of different ways of doing it. One way is that we could have a couple of lines here. There's a supply and return line that allows us to have not in line with the piping system. So one of the challenges that we're faced with, and this is where we're going to ask for Ron's expertise. I believe, Ron, we publish a limit for flow in GPM for each one of these guys for a certain size. Is that correct?
That's affirmative.
So in other words, and I don't have the numbers off the top of my head, so I'm going to make up a number. Please keep in mind I'm just making up a number just so you can get the general idea. If the main flow here was, say, 20 gallons per minute, I'm just making up some number here. We might divert 10% of that, or 2 gallons per minute, so that it makes sure it goes in the tank. There's the bladder inside there, get all that turbulence and make sure it's not stagnant and comes out. And so if the main has 20, across the bridge here would have 18, and then it would mix back with that 2, would have 20 back here again. So that's one way of piping it up. And that's if you're dealing with a large flow system and you're exceeding what we would publish for the maximum flow through the flow through expansion tank. So that's one option. Another option, I hope I've got it in here. Yes. Another option is that if you're within the flow limits of the flow through expansion tank, again, let's assume that the design of this has a limit of 20 gallons per minute through the expansion tank valve. That means that you could run it in line, so you don't have to have any piping in this little bridge over here. So there's two ways to install this guy. If you have a system, for example, that has a lot of flow and you just want to have a small amount going through the expansion tank, you can use the previous methodology, which we show here. Or if you have a system where you want to have 100% of the flow and the expansion tank is rated for that flow limitation, you can have the other little guy shown this way. So those are the two different ways of piping this guy. So it's very simple, very straightforward. Again, the largest source of stagnant water in an HVAC system happens to be the expansion tank. Okay, what else have we got here? So basically, like we said, it eliminates water stagnation, and we can purge the water circulating system of all the unwanted biohazard materials, such as Legionella, that sort of thing. The tank is NSF ANSI 61-G certified, which means we can use it in a domestic water system or potable water system. We can, all the connections are stainless steel. So in terms of what the water touches, it's all stainless steel. And it is a true flow-through design. Here's a sizing chart. I like to put this up there so that you can get an idea of what we're talking about. So in other words, let's say that you have an expansion tank and your system had a flow of, let me just look at here, see what the, yeah, okay, so let's say you had a flow of 100 gallons per minute. I'm just gonna make up a number here. So let's say that you had 100 gallons per minute in your main piping system here. We'll just put 100 gallons per minute. Oops. Well, that doesn't look like 100, right? That looks like they got sick there for a second. All right, so here's the main pipe going in here, and let's assume that that's 100 gallons per minute. Well, the expansion tank might have, in this case, let's just pick the small one and say it has a 55 gallon per minute maximum flow rate through the valve, in which case we would use that piping arrangement, which I showed you before. It's not the best place to put it. But anyway, if I had a main pipe here and that main pipe was 100 gallons per minute, I would divert 55 gallons per minute through the valve and then back to the main pipe again. Kind of see the flow arrows here. And I'd have to have some kind of valve here to create enough resistance so that my flow would get diverted. So we divert 55 gallons per minute through the expansion tank. Main system would have 100 gallons per minute. So it's quite easy to accommodate a limitation in terms of the maximum flow that we would have. And that's how you would set that up. Good stuff. So before I go any further, Brett, do we have any questions out there?
Yes, we have quite a few. So let's get started. I think the first question is related to sizing the expansion tank. How do you size the expansion tank for these conditions or for the flow through type?
So actually, it turns out you use exactly the same methodology that you use for sizing a conventional expansion tank that you would apply towards this. And we have a software on our website. And if we have a minute or two at the end, Brett, we can demonstrate that software.
Very
so
true.
Sizing the expansion tank is quite simple. The only thing we have to be very careful of is that if we're going to use it as a connected to the main, like I showed a minute ago, let's assume this pipe is the main right here. We want to make sure for whatever size expansion tank we're selecting that we don't exceed the recommended maximum flow. So in my simple example before, I said 55 gallons per minute. Other than that, that's the only difference between selecting a conventional expansion tank and then this type of expansion tank.
I just want to add, many of you on the call may be familiar with the TACO expansion tank model numbers. If you look at that list that Rich has on the screen, all of those model numbers, and Ronnie, correct me if I'm wrong here, are standard model numbers except with the F added in there. So as an example, that first one is a CAF 90-125. A non-flow-through tank would be a CA 90-125 that we sell to the industry on a regular basis. So just keep that in mind. Isn't that correct, Ronnie?
That is correct.
Yeah.
And I think those that first number actually is in the world of expansion tanks. I've always found this surprising. But if we have a tank that's a CA 90, that 90 represents liters. Is that correct, Ron?
That is also correct.
It's the weirdest thing. It's one of the few devices that uses liters as its kind of primary designation. And then, of course, in the next column, we tell you the gallonage right there. So in other words, a 90-liter tank is 23 gallons. If I jump down here to a 600-liter tank, that's a 158 gallons. So you get the general idea of what's going on.
Some people can test our math on their own. There's a conversion, gallons to liters. I hope that chart's correct. I'm sure it is.
Yeah, while you're chatting, I'm gonna test one out here while you're chatting there, Brett. See if we have any other questions.
So we have some other questions. Chet asked a good one here, and you kind of touched on it. And is this intended for potable hot water systems?
And the answer is yes.
Probably its main reason for coming out with it would be potable hot water systems. Wouldn't you agree with that, Ronnie?
Absolutely. That is the primary reason and the primary goal behind this type of design within an expansion tank is to minimize the possibility for stagnation, which unfortunately can lead to bacteria harboring and growth by putting the the multi-port connection on the expansion tank. We're able to force that flow all the way through the expansion tank with having it regularly flush out.
Excellent. And
so Brad, I did a quick test on my. I have one of those apps on my phone, and it works. It's amazing. So I just plugged in, for example, up 900. I put it in my little app here. It says 900. That should be 238 gallons. And what does it say here? 900. Look at that, 238 gallons.
Sweet. I knew that chart was correct. If Ron Falcon was involved and others, I know it was correct. So Mario Silva's on. Hey Mario, how you doing?
Hey Mario. What's up, man?
Stands for captive air tank, correct? And that is correct. So just to clarify, are flow-through expansion tanks full acceptance or partial acceptance?
They are full acceptance.
Full acceptance. How do you measure the flow through the tank in the bypass situation?
That's a very, very good question. That's an excellent question. So let's assume for a moment, let's go back to the other diagram. It's a little easy to see here. Let's see. Let's do it this way. Yeah. Okay. So can we get rid of that? Can we erase that? All right. So so here's the thing. If you have a main system here and you know that main system is 100 gallons per minute, I'm just making up some numbers here. And let's say the bypass through the tank is going to limit you to 55 gallons per minute. So you can put in one of those circuit setters. I think do we call them circuit setters? Do we call them, we have a different name for them, don't we?
I believe circuit setter is one of the names.
Yeah, and so you could use that little guy, you connect it to a gauge, and that will tell you what the flow is in that branch. And then you adjust this valve to make sure that you have, in this case, if you had 100 gallons per minute in the main and you're diverting 55, then that little, you would adjust that valve to get a reading of 55 down here. So that's how you balance it.
I mean, people are asking, how do you know that there's water being diverted through the tank? And it's really a science at this point, right?
Well, you know, it's a matter of measuring. I mean, if you put the device here for measuring and you do dial it in, then that flow is definitely going inside their tank.
So here's a question, Rich, that we usually divert to others. What is the cost adder for the flow through ET model?
Oh yeah, I always avoid the cost question. So on a rough percentage basis, maybe Ron can give us a rough idea of the percentage difference might be, just to kind of give us an order of magnitude.
Yeah, like you said, that's always one of those questions that we divert a little bit. Things can get a little goofy, location to location, territory to territory. From a cost perspective, we're probably looking at about maybe 7 to 8% higher than the normal cost for a standard single port model.
Yeah, and again, I think the important thing to keep in mind is that when we say that the cost differs from location to location, because it depends on, you know, freight costs to go from the factory to the destination. It depends on the tax structure. It depends on insurance, all kinds of things that you know, us mortal people don't get involved with. That's why we're not pricing experts.
To be quite honest, based on the numbers Ron just said, right, less than 10%, 7, 8, whatever, from a peace of mind thought process for making sure or preventing the possibility of Legionnaire or other stagnant water issues. I think it's, I won't say it's a no-brainer, but it might be easily accepted by folks on the design team and construction team and the owners of buildings and whatnot. At least in my mind, right? Wouldn't you agree with that, Rich? I mean, you've been involved with a lot more projects than I have, but good God, that's, you know, geez.
Yeah, you know, I think the thing to keep in mind is that we're not experts in biohazard material. We're experts in moving fluids through devices and things like that. And we've been, you know, we work closely with the, you know, the NSF groups that are out there and so on. And the bottom line is that we know that a device like this, because it's a flow-through device, it eliminates stagnation, and that is a positive thing. How it actually affects the quantity, the number, the, you know, all that, that's not our area of expertise. Our area of expertise is to make sure that we're providing circulation and not making, you know, and offering a non-stagnant. That's kind of a double negative, right? Non-stagnation. Let's put it the positive that that we have a flow through. That's the name of the expansion.
There you go.
Flow through. Okay.
Does diverting the water, and we might have to divert to Ron on this one, to the expansion tank have a higher pressure drop? I think we did some measurements on that, right, Rich? Ronnie?
Yeah, so we did testing to verify what the pressure losses would be that are seen. And of course, as you can imagine, there is some level of it. At the recommended flow rates, we were in the 3 to 4 PSI pressure loss range. However, what we did was compare our pressure loss up to one of our largest competitors in this market, and we were about half of what they were seeing for pressure drop.
Does the flow-through tank have a minimum flow? Good question, Chet.
So no, we don't publish a minimum flow. What we did during testing was to lower the flow and work its way down almost to no flow. And what had happened was that the result was a longer turnaround time to circulate the fluid. The time frame was extended, but still we were circulating fluid through that tank, which was the ultimate goal.
And I'm not sure how I'm going to ask this question. We're going to have to maybe team up to answer it. Michael's asking, this would be a good option as a domestic water drawdown tank for a booster system, wouldn't it? I'm not sure.
In my opinion, it could be utilized in such a system. The calculation for sizing it as a drawdown tank is going to be a little bit different than it would for just a typical thermal expansion tank calculation, which we currently use for these tanks. But if that were to be a request that someone had, we'd certainly like to look at that and size it up and see what we can offer.
And Rich, can you go to the page or on your charts? Excuse me, I'm a little off kilter here today. I haven't been involved. But anyways, your screen that shows the NSF code, because someone is asking again, is the flow-through tank code NSF requirement for potable water?
Well, that's a great question. We comply with NSF and ANSI/ANSI 61-G, but is it required by code? That's an excellent question. In other words, is it absolutely required by code? And I don't have an answer for that. And I'm going to write that down, so look that up.
And our friend Jim Prisby's on, Rich and Ronnie. Hi, Jim. I haven't talked to you in a while. Some codes may require the location of a thermal expansion tank to be a certain distance from the water heater. I think Jim is just making a statement there to make people aware of that. So be it.
You know, one of the things that whenever something is, you know, like in this case, it's an NSF 61-G certified tank, a lot of times it's up to the local authority. What's the term that we use? We say the authority having jurisdiction. AHJ, authority having jurisdiction. Yeah, the AHJ has the final word, and they can, even if there is no state or local code that, I'm sorry, the requirement to meet a specific thing in the written code, they can just simply add that as a requirement because they have that authority to do it. So, you know, the cost of providing this type of protection is so small. Like Ron said, probably less than 10%. It's well worth considering.
Here's a question. Is this patent pending contraption available for a retrofit for an existing tank?
That's a great question. I don't think we can retrofit. It wouldn't meet our ASME standard, right, Ron?
Well, so we could provide it as a U2 component where it could bolt onto an existing single port expansion tank, depending on the year. So we would want to look and make sure, you know, that it is in fact compatible. In most cases, it would be. The biggest concern that could come into play, and I doubt anybody would really notice, is that the model number that is used on the nameplate, which is on the body of the expansion tank, might not or wouldn't, if you retrofit that onto an existing tank, the model number wouldn't reference the model number of a certified flow-through tank. So what I mean by certified is an NSF ANSI certified. So it may appear based on the model number that it's not certified, and it wouldn't actually be certified because the model number didn't reference the proper model number, but it would be using all the certified materials.
So there's a good chance that an existing TACO CA expansion tank, captive air, full expansion tank, would be retrofittable. Is that a good word? I have no idea.
That word. Say that word 3 times fast, Brett.
You know, I think I just seen some new words in the dictionary on the TV. So there's one they could put up there. There's a good possibility you could do that. But what Ronnie was just mentioning is somebody came by looking at the codes, that model number may not reference that. So you may need to get a new nameplate or something to that effect, possibly. So I'm not sure that is a case that's going to be done too often, but nonetheless, great question. Here's another one, Ron. What is the maximum working pressure? 1,000 PSI? I know we go high.
Yeah, so I guess what can you dream of, right? So we can do these, we have standard designs for 125, 150, 175, 250, 300. We've just quoted out some 400 PSI designs. What do you need?
There is no limitation. Well, there's, I should, sometimes when you say a definite like that, it's difficult, but if you have higher than 400 PSI or higher than our standard of 300 PSI, contact your local TACO rep, who will get in touch with the fine folks in Fall River, Massachusetts, where these are manufactured, and they will look at putting a design together for higher pressures than what we catalog. So, bingo, bango, bongo. We're getting near the end, Rich. We did a lot of questions. Great questions today.
We're just about approaching 1 p.m. East Coast time. Do you have any other questions out there that we can help people answer?
I'm sure there's some. Well, right now the questions are behind us. I don't see any new ones popping up.
I have a question for the audience, and that is that what's everybody want for Christmas this year?
My two front teeth. No, that's a song, right?
That's a song, yeah. So when my kids ask me what I want for Christmas, I always say I want the gift card so I can go to Lowe's and buy tools.
Winning lottery numbers. That's a good one, William. That could be a tough one.
That's a tough. Yeah. Can you imagine? I guess there was what was it, a month? Just about. Well, I don't know if it was a month, but several weeks ago,
$1 billion.
$2 billion prize was won by one person, and that was out in California somewhere, right?
So,
do we have
Chris,
anybody online here? Do we have anybody out in California that knows the winner?
Chris said frisbee golf basket. I like that. You ever hear that? That's another new sport out. Well, not new, but people play frisbee golf, and Chris is looking for a frisbee golf basket. We'll have to let someone in his inner circle know about that. I don't want to brag to the audience, but I'm going to brag anyways. I could put up on my computer right now a picture of our Christmas trees already set up, decorated, with all the presents wrapped underneath it, ready to be distributed. What do you think of that?
You started early this year, Brett.
Ahead of the game. Well, there's reasons for that, but nonetheless.
I understand. Hey, listen, we're just about at 1 o'clock. If there is a last minute question, we'll squeeze it in. If not, I would like to take this time to thank Ron helping us out today. Appreciate it, Ron. I really, really do. And I'm sorry you had so much computer difficulty at the beginning, Brett, but thanks for hanging in there and getting on there with all of the wonderful stuff.
It was a team effort. IT got right back in touch with me, and the TACO IT folks, and whatever. It's behind me.
So at this point, I'd like to wish everyone a happy holiday season, and hopefully they, if they're interested in getting Christmas gifts, or it doesn't have to be specifically Christmas, any kind of gift for this time of year would be welcome. I hope they get what they're looking for. So with that, I'm going to say thank you, Ron. Thank you, Brett. And unless you have some last minute words, Brett, I'm going to say take care. And how does that little story? And to all, a good night.
Yeah. Before we sign off, Ronnie, you want to say goodbye and good wish to everybody before we sign it off?
Thank you all very much for the opportunity. Thank you for jumping in and being part of this call. A lot of great stuff going on here here at TACO, and thank you again.
Thanks, Ronnie. Appreciate it. And don't forget, folks, look for your email tomorrow. The most of you have been through this rotation before. Roughly 24 hours. A copy of the today's presentation. Of the filming or the video of it. And also, if you need your PDH hour, the certificate will be attached. So signing off, the commercial team with big help from Ron. Take care, and we will be in touch down the road. Take care, everybody. Goodbye.